Hello, we're Team Autonomous Meteor Detecting Radio Telescope, a multidisciplinary senior design team in the Kate Gleason College of Engineering. We're collaborating with the Lancaster Amateur Radio Club to address the limitations of optical meteor detection caused by cloud coverage and daylight conditions. Our stakeholders are interested in a robust and cost-effective solution that can operate independently and provide detailed information on meteor events, regardless of Western New York weather.
Our problem statement is to create a concept to detect meteors not constrained by local weather. In New York, that's a lot of cloud cover. Our requirements are to find meteors using reflected RF of distant commercial FM transmitters, and then also to provide an internet portal for sponsors and users to view our data. And our solution is our radio telescope. So here's a quick diagram of how this works. Essentially, when a meteor comes in through the atmosphere, it creates an ionized cloud. This will reflect a distant FM signal, which then will be picked up by our receiver. And this will happen over the Earth's the curve, so it'll be out of line of sight.
So for our proof of concept design, we have some engineering requirements. First, we want to receive the FM broadcast band between 88 and 108 megahertz. Have two antennas, one for the distant city stations and one for the ambient noise and local stations. Also have a antenna rotor that is 360 degrees. Have embedded software that manually positions antenna, and then create a visual representation for the data. Power the device through 120 volts and operate regardless of the temperature and weather conditions in Western New York. So here we have two flowcharts to kind of explain the steps that were taken or that we hoped would be taken for the antenna to receive meteor signals. So the top one shows the overall steps for the meteor detection and how we determined what distant cities to receive from, as well as which stations to, and just the overall what would occur when a meteor shower is happening. The bottom one is a more close in-depth look at the hardware communication, and pause now if you would like to read more about it.
So when verifying the presence of a clear channel that is blank, you can use the 360-degree halo dipole antenna, and you can look to ensure that there is an area without any signal peaks. Each peak in this diagram represents the presence of an FM station, and so you look for where there is no FM station, and then to test the performance of a device with no FM station, you can use a low-power FM transmitter to simulate the DX reception from a meteor reflection. And you can use RDS to identify the actual channel and the broadcaster.
And going into the electrical hardware, we have a handful of items that we actually use to build this section up. This includes the Raspberry Pi, an SDR, an Arduino, the H-bridge motor driver to drive up the signals from the Arduino to the motor controller, the AC power, a Yagi log periodic antenna, an FM halo antenna, and the Yaesu rotator. And here we have a current wire diagram of everything, of all the electrical components. You can feel free to pause and take a closer look if you'd like.
Mechanically, our product consists of the following main components. We have the log periodic antenna, which is the big directional one on top. We also have the omnidirectional dipole antenna, which is referred to as the halo in this presentation. We have the manual altitude adjustment mechanism, the azimuth rotator, the weatherproof electronics enclosure, and all of this is attached to a steel antenna mast. These are some close-ups of the computer-aided design or CAD model of the system. And here are some pictures of the actual assembled prototype. One challenge we encountered and overcame during this process. So we ran out of budget during the initial design phase for a 2-axis rotator. This meant that we couldn't point exactly at the meteor showers. So our solution is to have a 1-axis rotator, which allows us to rotate in azimuth, and then a manual adjustment for the altitude. With this, we can leverage the 45 degrees of sensitivity from the directional antenna, and it allows us to listen for all but 2 major meteor showers during the year. So this taught us how to be resourceful and how to make engineering compromises to deliver the max functionality with the given constraints. We just want to extend a thank you to all these people who contributed to our project, and thank you for listening.